Good afternoon, everyone. Welcome to lecture 5 on finite element method. In this lecture, we want to pick up where we left off in the last lecture, and we want to talk about two concepts, basically. The first concept is the so-called static condensation and a reduced system. And its connection to what we call a reduced system. And this is something we almost finished completely in the last lecture. So I will just have more or less like a reminder of that. The second topic we want to talk about is the so-called extended node list. So ENL for short. Okay, so we want to talk about this thing that we call extended node list. Now, this concept of extended node list, as I mentioned, it is some sort of, let's say, invention that we have in this course. It's not something very standard. It's not something very non-standard either. I think everyone can do it in a different way. This is the way I find it straightforward to implement and to teach. Okay, but let's say after a few lectures and weeks, when you are comfortable with that, maybe you can also come up with your own ideas and your own inventions of how to order the nodes. So the idea is to order the nodes. I will start again with a short overview of what we have done to bring us where we are today. So remember, we started the lecture with this assumption that a spring is a good representation of a finite element, of an element in a finite elements method. And then based on that, we said, well, you can write the spring system as F equals KU. K is the stiffness matrix, U is the displacement of the nodes, and F are the external forces on the nodes. And then if you can write every single spring like that, we also talked about different combinations of springs, so you can assemble different springs together. And then in the last lecture, we talked, or let's say we opened the discussion on how to do this assembly in a less intelligent way. So we learned how to do it in an intelligent way, or how to do it in a way that you know the number of degrees of the system, and then let's say if it is 10, you can visually see it, you can draw it. Now we want to extend that idea to a, let's say, approach where we do not necessarily know how many nodes we have. We can have large systems and we don't need to include our, let's say, our human intelligence to it, so that we can later program it. So we are looking for an algorithmic approach to the problem. And then towards that algorithmic approach, we had this concept of global node numbering and local node numbering. And that is also an important part of the process. So we need global numbers for nodes. And then again, these are usually degrees of freedom, but in this case, we have one-dimensional problem. So we are dealing with global node numbering. And then we looked into this example together, and we drew, or we wrote the stiffnesses for each of the elements. And then we explained that, for instance, if we use these numbers for the nodes as the global numbers, you can now associate each of these elements. For instance, if you think of element 2 here, is between node 2 and 4. So these 2 and 4, they come here. So basically, you can just do it and then combine these little stiffnesses together. And then, as I said, this combination, this word that I use as combine, it basically is what we call assembly in the finite elements method. So you end up with a system that looks like this. So you would have on your left side your force vector, you have your stiffness matrix, which in this case is 4 by 4, and then you have your displacement vector. And then their dimensions, in this case, it's basically number of nodes times 1. number of nodes times number of nodes for the stiffness, and number of nodes times 1 for the displacement. And as we mentioned previously, this number of nodes is in general problem dimension times number of nodes. And here it's 1D, so it's just number of nodes. But then we also discussed the boundary conditions on the system, and we introduced two types of boundary conditions. So we need two types of boundary conditions in a usual mechanical problem. In a mechanical problem, either you apply a force or a displacement to anything, right? So either you take something in your hand and you deform it, and then you just measure how much you deform it, and you don't know how much force you applied, but you can calculate the force. Or you have some sort of force gauge, or you apply a weight to it, so you know how much force it is, and then you can calculate the deformation. So the first one, where you apply displacement, is the so-called Dirichlet type boundary condition. And the second one is the Neumann type boundary condition, where you apply a force. Now, obviously, as I mentioned, where you apply, or when you apply a force, you don't know the displacement. When you apply a displacement, you don't know the force. So you cannot apply both of them. Either it is Neumann or Dirichlet. And in the problem that we had, it just happens that the first node on the left, it's a wall, it's a fixed wall. That means displacement is 0. So it's a Dirichlet type boundary condition. And it's a homogeneous Dirichlet, so it is 0. On the right end, you apply displacement also. So at node 4, you apply a displacement, which is also a Dirichlet type boundary condition, as we discussed. But now the prescribed displacement is not 0. So this is what we call a non-homogeneous Dirichlet boundary condition. Now, obviously, on nodes 2 and 3, you don't know how much displacements you have. So these are unknown displacements, but then you know how much force you apply on them. In this case, you don't apply any particular force or any external force. So the forces are just 0, which means these are homogeneous Neumann type boundary conditions. So now if you look at our system, again, if it is 4 by 4, just looking at this system, you can solve it. Okay, so manually you can just solve a system like this. But you need to go through certain steps to do that. But then we discussed if only if we could just reorder the nodes differently, then solving this system would be much easier. So what do I mean? I mean, if we could number them such that these two nodes, the unknown displacements, they came on top, and these two, the known displacements, they came at the bottom. Okay, so we could reorder them such that we get this system. This system is much nicer to solve, because then you can basically have your degrees of freedom on top and then your constraints at the bottom. And then if you have a system like that, we just discussed that you can basically do this little manipulation here, and you get a system which we call a reduced system. And that reduced system has the dimension of just KPU here. Okay, so it's a smaller system, so it's easier to solve because it's smaller, but also because the nodes are ordered nicely. You don't have to do all these matrix manipulations in between. The solution is just straightforward. You end up with a system which looks like that. And as I mentioned, this thing is called reduced system, and the process where it takes you to this is the so-called static condensation. In the case of our example, this would mean that, for instance, if we number them like that, we get this system. We discussed this, but in this case, it means if we just used a different numbering like this, then this would have worked for us. We would get a system like this automatically, free of charge, basically. And here, this is the question. We want to do this process efficiently. Okay, so we know that these node numbers 1, 2, 3, 4, these are just the node numbers and these are coordinates. Okay, the question is, what degree can we assign to them such that they give us a system like this automatically? This is where we ended the previous lecture. And as I mentioned, this brings us to the topic of extended node list. So we want to introduce some information to those node lists or to those nodes to get basically the system that we want automatically. Now, that brings us to the topic of today's lecture, basically, or what we want to now go into details, extended node list. So I'm going to just remind you again of what we had. In this picture, the numbers that you see here, the node numbers are just node indicators. Okay, so if you think nodes are people, these numbers, they are only their names. Okay, but the degrees are something like their IDs. It's an ID that is defined after naming them. Okay, so each person has a unique ID, but then again, this is a secondary information that we can assign to those nodes. Now, in order to explain this extended node list, every year I teach it slightly differently, but this year I have a very nice example, and I think this is a very meaningful way of explaining it. So let's just start with a little game together, or with a little puzzle. So let's say we have a few people. So I'm going to just duplicate this person in a line. And then again, this example, although it's just a very simple example, I think it is very much representative of what we are going to do. It's a perfect example. So I think after this example, you should have a very good understanding of what you need to do to construct the extended node list. Okay, so think of this line of people. Okay, so this is again just a little game that we play together. And we have how many people? Again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we have 11 people in the line. See, I just counted them to be 11. If they are a million, I wouldn't be able to count them. So this information that I just mentioned, we usually don't have it. Okay, we just know we have a bunch of nodes, which could be a bunch of people. For simplicity, I just counted it so that I know what I'm doing, but we don't necessarily know how many people we have. Now, each person has a name. Okay, so each person has a name, which in your node list would be the node number. Okay, so this would be, again, because these are like people, I am going to just call them maybe A, B, C, assuming that these are just their names. Okay, and as you here again, I am just starting from A to K, but the order doesn't matter. They could have any names. Okay, this is important. The naming is completely arbitrary. So the naming, which in your case, and that goes back to the question that one of you asked at the beginning, in your case, if they are nodes, it means the numbering is arbitrary. Now, here is the game. We want to count a few things. We want to count how many people are in the queue. So how many people are in the queue? We want to count that. And let's say each person is either right-handed or left-handed. We want to count also how many right-handed people and how many left-handed people are in the queue. How many right-handed? And how many left-handed? And that's not all of it. We also want to assign a number to each right-handed person and assign a number to each left-handed person, such that once they know their numbers, they can switch their places, and all the right-handed people, they come to the right-hand side, and all the left-handed people, they go to the left-hand side. Okay, so we are also looking for, let's say, give them, assign. Now, these numbers, I call them degrees. You may have a good feeling why I'm calling them degrees. So we assign degrees to these people. And then we want to assign these degrees such that we end up with a queue that looks like this. Let's say you have all the people. We want, okay, let's say we have more right-handed people than left-handed people. We want to have this queue to be split into two parts. All the left-handed people, we want them to be, let's say, on the left-hand side. And all the right-handed people, we want to be on the right-hand side. Does that make sense? So this is what you want to do. You want to count how many people you have. You want to count how many right-handed and how many left-handed people you have. And then to each right-handed and left-handed people, you assign a number such that if they took those numbers, all the left-handed people, they end up at the beginning. All the right-handed people, they end up at the end. Okay, so this is not complicated when you just look at 11 people, right? You can do it. It's a doable task. There is a catch. So we want to do this in one loop. Okay, we don't want, if we have 11 people, of course we can go to 11 times into a loop and then keep counting what's going on and then eventually do it, right? But then if instead of 11 you have 11,000, that becomes extremely complicated. So that's the catch. We want to do it in one go, okay? Which in this little puzzle that I have designed for this purpose, basically, it means that each of these people could just say one thing, okay? So every person knows if he is left-handed or right-handed, okay? So every person knows, as you can imagine, every one of you knows that if you are left-handed or right-handed. But that person can only just say one word, okay, or one number or anything. I mean, there is no communication between these people. Everyone can just say one word. And that is the, let's say, the condition here. So the condition is that every person can say one word. And that word could be a number, but that's it. Now, again, this condition of every person one word, if you want to program it, it translates to having one loop, okay? So from programming perspective, it means you just have a loop from person 1 to person n. Okay? in programming language, that means it is just one loop. All right. So as I mentioned, this is a kind of a game I have designed to explain this. Do you understand the question? Is there any misunderstanding of the problem? The problem is really clear, right? I don't know if any of you has an idea of how to do it. I mean, if in usual classes, I think we just play with this or with different ideas a little to see how you can do it. And you can think about it on your own to come up with your own ideas. I am sure there are more than one way of doing this. And now we want to do it together. So I want to sort of explain one way of doing this, which is going to give us the answer quickly. Now, before that, just for the purpose of having the game or for the fun of the game, let's say we assign who is left-handed and who is right-handed. Okay, so let's say right starts with the letter R, so I'm going to make them red. Okay, so I just take a few of these people and I make them red. These are the right-handed people. I don't know, let's say this guy is right-handed, the B. Maybe these two are right-handed. And then maybe these two are right. Oh, well, this one is right-handed and the last one is right-handed. Okay, so the right-handed people are red. And this is, again, this is just a little color indication for ourselves. But in your finite element method, left-handed and right-handed, it translates to be Neumann boundary condition or Dirichlet boundary condition. So that's one thing. The other thing is that every node knows if it is Dirichlet or Neumann. Like every person knows if he is or she is left-handed or right-handed. Okay, so let me just add that information. So basically, in view of what we do in a finite element code, left-handed people are like Neumann type boundary condition eventually. And right-handed people are Dirichlet type boundary conditions. Now, why do I say these are, or left-handed are like Neumann and right-handed are like Dirichlet? It's because of the way that I just mentioned we want to order them. Remember, I said we want to put the right-handed people at the end and left-handed people at the beginning. If you remember, again, from just what I said previously, this is what we want to do. So we want the Neumann type boundary condition at the beginning and Dirichlet at the end. So let's say in view of our example, it means right-handed people represent Dirichlet type boundary conditions. All right, so I think the example is clear, or the question is clear, the task. And what we want to do is to just now answer it and end up with a nice way of doing it. And this is what brings me to the concept of extended node list, or how we generate these degrees. So this is what I propose we do. And that is kind of the answer to this. Maybe it's only one answer. Maybe you also come up with your alternative answers. But this is one way of doing this. I tell these people, so let's say these people have a meeting and one of them is smart and then he comes up with this idea. So they can say one word, right? And you start either at the beginning or at the end. So you come to this person, and this person, again, he knows if he is right-handed or left-handed. If he is right-handed, he shouts a minus number. If he's left-handed, he shouts a plus number. And they start from 1, okay? So let's say if this guy is right-handed, he is in this case left-handed, right? So in this case, he's left-handed, he would just shout 1. This guy, he's right-handed, he would shout -1. Then this guy, he has heard the 1 and he knows he's left-handed, so he adds 1 to it, so he would shout 2. Then the next guy, he has heard the last negative number and he's right-handed, so he will shout -2. The next guy would shout -3. Then this guy would shout 2. Sorry, this guy would shout 3. This guy would shout 4, 5. Then what was the last negative number? -3. So he adds 1 minus 1 to it. So it would be -4, 6, and -5. So if you look at what just happened, you basically now have these nice numbers associated with the left-handed people, which is 1, 2, 3, 4, 5, 6. And then all you have to do is to just add the absolute value of the negative numbers to the maximum number of the yellow numbers. So your -1 person, it becomes 7. Okay, so what I'm trying to say, let me just write it again, maybe in words. So this person shouted what? This person shouted +1, right? Or 1. And this guy shouted -1. So this shouts 2, -2, -3. Am I going right? Yes. 3, 4, 5, -4, 6, and -5. Okay, and as I said, once they do this, now all the left-handed people, they have their correct numbers anyway. So they are 1, 2, 3, 4, 5, 6, which means they are in the first half of that range. And then you know the maximum plus number. So this guy would just add, I mean, he doesn't have to do it. This is already in your list. Okay, so when you do your matrix, you already have it here. So these guys are already there and these guys are already there, but just to make them clear that how these numbers would work, I'm just adding them, let's say manually, or we add them manually in our MATLAB code to make it clear. Otherwise, we really don't even have to do this step. Or these people don't have to do this. They already know the information they were looking for. So that means if you think of the global degree, this guy would have the global degree 1. This guy would have the global degree 2, 3, 4, 5, 6. These are their global degrees, okay? And once you are here, as I mentioned, you know now the maximum positive number is 6. So you just add the absolute value of negative numbers to that. So this would be 7, 8, 9, 10, 11. Okay. So now basically you already have these nodes assigned, or these numbers assigned to your nodes in one loop, by the way. And you can already see that if these people, they just pick up these numbers and order themselves, the tasks that we have is now done. the maximum number that you see is 11. So we counted automatically how many people we have. We counted how many left-handed people we have because that is the maximum positive number. We counted how many right-handed people we have. That's the maximum negative number. And we also assigned them a node such that they can order themselves according to what we wanted. Does that make sense? Again, this is just a game. I think you may say it has nothing to do with finite element method, but this is, in my opinion, or at least until now, this is the best way I can explain what we want to do in this, let's say, automatic ordering. Okay, we want to just go through this, and then again, in this example, if you think of it in a sense of a finite element method problem, the number 6, the maximum plus number that you have, is number of degrees of freedom. Degrees of freedom, we call them DOF. So 6 is the number of degrees of freedom. 5 is the number of degrees of constraint, we called them previously, right? Because -5 is the largest number. So minus means constraint, and the number just basically shows the location of that. So what I'm trying to say is that in a finite element problem, you would have this type of scenario. You have a bunch of nodes that they have names or numbers, and each node knows if it is Dirichlet or Neumann. In this case, it would mean if it is right-handed or left-handed, respectively. But what we want to do now is exactly that. We want to kind of do the same example as if we just did this, but now we do this assuming that we are dealing with nodes. And I ordered them nicely so that you can see what's going on. Okay, so let's say you have a system. It doesn't matter which system it is, but it is, I mean, since I have it in this lecture, why do I not just copy it? It's actually exactly the system we had here. Okay, so wait a second. Okay, no, it's not this system. It's a different system. So I'm not going to draw the system. I just write the information. So again, node list is usually something which has node number and coordinates. Okay, so you would have a node list. And let's say we have a system, it doesn't matter how the system looks like, but we have a system that has, I don't know, 5 nodes. And in front of each node, you have coordinates. Okay, again, in this example, if it is a 1D problem, these coordinates are just X coordinates. So they identify the length of that string or element. But if it's a 2D example, this would be X and Y. It doesn't matter. It's eventually some information you have about those locations. Now, each node has some information about its boundary condition type. So each node knows if it is Dirichlet or Neumann. Okay. Now, for simplicity, let's again just assume, I don't know, the first one is Dirichlet, and then maybe the next one is Neumann. The next one is Neumann, maybe. Then we have one more Dirichlet and one more Neumann. So these are the information. And as I said, these information would be like being left-handed or right-handed. Now, you would have this temporary degree of freedom, or temporary, let's call it temporary degree. This is like those numbers that those soldiers or those people in the queue, they just shouted. So you can have its temporary degree, and then we would eventually have the real degree. So remember here that the trick was you start, it's like I write it like a little loop here, by the way. Let me just, so think of this thing as a loop. When you want to program it, it really works like this. You would just say, well, I start with something that I call DOF, and I set this to 0, and then I start with something that I call, I don't know, DOCs, and I set it to 0. And then you would have a loop. You would say if your node type is Dirichlet, then you do something like this. You would say DOCs is DOCs minus 1. Okay, this is like those people shouting -1 and adding -1 to themselves. And then if it is Neumann, then that DOF is just DOF plus 1. Okay, that's pretty much it. This is exactly how you are going to program this. Okay, and now I again keep this on the side. So this is like a little algorithm that you can just use to assign the temporary degrees. So let's put it on the side, and then we do this temporary degree together right now. So you come to node 1, and then DOC is 0. It's Dirichlet, so your temporary degree would be -1. Then the next one is node 2 is Neumann, so temporary degree would be +1, or DOF basically +1. Then 2, then -2, and 3. Okay, and then again, once you are here, you can clearly see your system basically has 3 is the plus number, so that is your degrees of freedom. You have 3 degrees of freedom and 2, let's say, degrees of constraints, which is no surprise. This is what you had. I mean, again, as long as it is 5 and it's on one paper, you can obviously see there are 2 of them, and there are 3 of them here. But if it's a million, you cannot just count it like that, but your little algorithm can. And once you are here, you know exactly those informations, that information. So now that you are here, all you need to do is to basically fill out the degree. And as I mentioned, if the nodes are having a plus number, the degree would be the same as temporary degree. If they have a minus number, the degree would be the maximum plus number, which is DOF, plus absolute value of temporary degree. Okay, so you would have here 4, 1, 2, 5, and 3. Okay, and as I said here, the trick is again this little algorithm. Basically, you would just check. I mean, if your temporary degree is positive, so if temporary degree is positive, then degree is the same as temporary degree. If it is negative, so otherwise, you would say degree is DOFs, which is the maximum number of temporary degrees. And at this point, you know them anyway. So it's DOFs plus absolute value of temporary degree. Okay. And once you do that, you get this numbering. Does that make sense? So again, this would be a sort of, let's say, hypothetical system. What I'm going to do in the little remaining time is to just go back to our previous example, the one that I mentioned, and we want to see if now we can number that using the same algorithm together and see how far we go. So let's say we don't have any of these. Okay, so let's say we have this thing, and then we want to do it for the system we started with. Okay, so this is our system. Now let's play the same game. Now, node 1 is a Dirichlet node, right? You can see it here, it's fixed. So it's a Dirichlet. So this is Dirichlet. This is Neumann. This is Neumann. And this one is Dirichlet too. And we want to do exactly this. Or we want to add these informations. So it's Dirichlet, Neumann, Neumann, Dirichlet. Now, based on what we have and this little algorithm that we had previously, so let me just also copy this algorithm for us. Based on this, you can play the same game again. I understand this game is extremely simple right now because it's 4 nodes and you can see everything. But once you program it, you can understand the, let's say, the potential of this and the reason we are spending so much time on it. So if you do this now, your temporary degree would be -1 for node 1. Then you would have 1, 2, -2. And then you do the other little algorithm that we had, this purple algorithm here. Okay, so let's say this is the purple algorithm here. And now if you do that, or if you use that, you know, when you are here, you know you have DOFs is the maximum number. So it's 2 already. So basically here you get 2 plus 1. For the first one, that would be 3. 1, 2, 4. Okay, so what does this mean? This means your node 1 should have the global number 3. Your node 2 should have the global number 1. Your node 3 should have the global number 2. And your node 4 should have the global number 4. Okay, and if you did that, then you end up with a system which looks like this. You would have KU equals F. Okay, I'm writing F on the right-hand side. It doesn't really matter. But you would now have a system which looks like this. Exactly, the one that we wanted. So this would be your KU equals F system. And now in this system, on top, you have all the Neumann boundary condition. At the bottom, you have all the Dirichlet boundary conditions. So you can already see it, right? So 1 and 2, they would be this upper part, and then 3 and 4, they would be the lower part automatically. We kind of, again, from a conceptual perspective, we predicted that. See this picture? This is from our previous picture, from our previous lecture. So we kind of, in the previous lecture, we predicted that if only if we could assign these degrees, we wouldn't have had, well, we wouldn't have had to play that game. So we could have just had our reduced system automatically free of charge. And that is the answer to this question. Okay, so remember at the beginning of this lecture, I mentioned that what we want to do today is to introduce a new concept, or again, an invented concept of extended node list. We want to extend our node list such that it delivers this information for us, And we just answered that question, okay? So now we automatically get exactly what we wanted to get from the previous lecture. And as I mentioned, I just did this with, let's say, with this example of a few soldiers in a queue or something like that. But this is a very meaningful way of explaining of what we do, in my opinion. And if, again, once you program this, and I don't know if you have watched the videos for programming, this is also what we do for programming. And then later that we do 2D, and even if you want to do 3D finite element, this part of the problem remains always identical to what we did, okay? Except that, again, if it is 2D, you can imagine in front of each node, you would have two information maybe, because one would be the boundary condition in the X direction, in the Y direction, but eventually it would mean the same thing that we did before, except that maybe we also ask these people if they are right-handed, left-handed, and then they play soccer with right leg or left leg or something. So each person has two information. It's eventually exactly the same game that we play. All right. So this is all I wanted to talk about exactly for this lecture. So we are exactly where I wanted to be. In the next lecture, we would discuss this for a trust structure in a two-dimensional system. So again, remember at the beginning of the course, I said when we say one-dimensional problem, it means one-dimensional element in one-dimensional space. But now each of these trusses, they can also rotate in space. So we could have one-dimensional elements in two-dimensional space. That's what we want to talk about in the next lecture. Very good. Do you have any question? Thank you very much for your attention.